Okay, now we're doing independent and dependent events. So, what is that, you say? Here we go. Independent and dependent events. So this is on page 499. 499. So, independent events are where you do something that has no effect on the second thing that you do. So, for example, if I'm spinning a spinner, like this one, if I spin it, if it lands on red the first time, when I spin it again, that has no bearing. It could still land in red, or it might land on green, or it might land on blue. The spin is independent of what's happening, right? Because the first time I spin it, it can land anywhere, and then the second time I spin it, it can still land anywhere. You know, there's no change. But if I have a bag of marbles, and I have 5 blue ones and 4 red ones and 1 yellow one and 2 green ones, right? And they're all in this bag. If I pick one, the chance of getting a blue one, you'd have to add all these up, 4, 9, 10, 12, there's 12 marbles. So the chance of getting a blue one would be 5 out of 12. Now, if you held that in your hand, right, then they're not 12 marbles in the bag anymore. Now there's only 11 marbles in the bag. So that if I choose another blue one, then there'd be only 4 blue ones out of 11 marbles, right? So it changed the probability because what I did affected the next choice. So that's a dependent event. So whenever it's independent, it has no effect on the choices at all. So in this one, if I had chosen a blue one, 5 chances out of 12 to get a blue one, right? And then I put the blue one back in the bag, stirred it all up, reached in and grabbed another one, then there's still 5 chances out of 12 that I get a blue one, right? So that's independent. If I put it back in, if I replace it, it's independent. If I take it out and hold on to it and then reach in and grab another blue one, that would be dependent, right? Or any marble. If I reach in and grab a different color, it doesn't matter. It's still dependent because there's less to choose from than you had before. So, let's see if we can do this. Let's look at this one. Okay, we've got a whole deck of cards. So I don't know how much you play with cards and stuff, but there are 52 of these guys. Let's see, that's too bright. Maybe this is a little bit brighter. Okay, that's better. So there are 52 of these cards, right? And they want to know whether doing the thing is independent, choosing a card is independent or dependent. So, if I take 2 aces in a row, when after the first card is replaced. So see, if you put it back in the pile, there's still 52 cards in the pile, and there's only 4 aces, so there's 4 chances out of 52 for the first one. And then if I put it back in the pile, then there's still 52. If I shuffle them and then pick another ace, there's 4 chances out of 52 that I did it right. So if I multiply those two together, I get this probability. Okay? Now, if I don't put it back, I don't replace the card, if I choose a card and then don't put it back and hold on to that card, then it's a dependent event. So if you don't replace it, it changes the number of cards. So here, there was 52 cards. When I put it back in there, there was 52. If I do it and just hold on to that ace and then say, now what's the probability? Then there's only 51 cards in the pile, right? And 3 of them are aces. So that would be a smaller probability if I held it. Let's look at this one. Selecting a face card. A face card, that's kings or queens or jacks, right? And so there's 4 different suits. So 4 different suits. There's 12 total cards. So I select a face card, and then I choose a 7. And so there's 4 different 7s. So there's 12 face cards and 4 7s, right? Now you may say, well, that's independent because you're not choosing the same thing like here. But no, it's dependent because when you pick one, if you don't replace it, see it says right there, no replacement. When you pick out of the first, there's 12 face cards, so you can get a king or a jack or a queen, you know, there's 12 to choose from out of 52. But if you hold on to that and you say, now what's the probability that I pick a 7? It changed because now this is 51 cards to choose from. And 4 out of 51 is the probability that changed. So that's this probability, right? So that's what we're shooting for. This one's dependent, this one's independent, right? All right, so let's look at a problem right here. Let's look at this one. So if I flip a quarter, if I flip a coin and I say, is it going to land heads or tails? So, flip a coin, is it going to land heads or tails? Well, the probability that he tosses heads is 1 chance out of 2, right? 1/2. What's the probability that he tosses tails? 1/2. What's the probability that he tosses heads and then tosses tails? 1/2 times 1/2, right? So, and means times. When you see the word and, you want to multiply. So this guy right here means multiply. Multiply, right? And then this was 1/2 of the time, and this is 1/2 of the time. And then it's totally independent because whatever I flip on this first time I flip this, it doesn't matter. The second time I flip it, it can be either thing, right? I didn't take away one of my choices, right? It's still there. So, where was I? 1/2 times 1/2. So that would be 1/4 of the time. He would have a head and then a tail, right? That's the way it works. Now if he tosses it 3 times, what's the probability that he'll get tails every time? Well, that would be 1/2 times 1/2 times 1/2, which would be 1/8, right? 1/8 of the time. Remember, you can make it percent if you want. This would be 25%. 1/8 is 12.5%. And like I said, usually they want it like that. Now, if you roll a number cube, remember that's just a dice, right? If you roll a number cube twice, what's the probability that you'll roll an odd number and then an even number? Well, the numbers are 1, 2, 3, 4, 5, 6. So there's 3 odd numbers. That's 1/2 of the time. And then there's 3 even numbers. That's also 1/2 of the time. So the probability that she'll roll an odd number and then an even number is, you could say, well, there's 3 odd numbers and 6 total numbers, and then there's 3 odd numbers and 3 even numbers and 6 total numbers. So that would be 9 out of 36, which is the same thing as 1/4 of the time. Now she rolls a number cube dice 3 times, right? What's the probability that she'll get a 3 every single time? Well, there's 1 chance out of 6 to get a 3 for the first one. And then there's 1 chance out of 6 to get a 3 on the second one. And then there's 1 chance out of 6 to get a 3. These are totally independent, right? Because once I roll it, and then I roll it again, and then I roll it again, the first roll doesn't have any effect on any of the rolls. So that would be 1 chance out of 216. That would be very, very, very tiny. So that'd be 0.5%, 0.0005, right? That's that. Okay, so let's erase these and look at the next little section here. Those are all independent. And then let's look at some that are dependent, right? That's what we want. Okay, so there are 3 apples and 5 oranges in a bag. So what's the probability of getting 2 apples when you don't, it says without replacement, right? So the probability of getting 1 apple would be 3 chances out of 8. Remember, there's 8 total fruits. You have to add these together to get the total number in the bag. And I pick an apple. And then what's the probability that I'm holding on to that apple, or I'm eating that apple, and then I reach in and grab another one? What's the probability that I get another apple? Well, now there's only 7 fruits in the bag, right? So this is dependent. So this would be 6 on top and 56 on the bottom, right? So what would that be? So 6 divided by 56 is 10.7%. 10.7%. Right? So 10.7% is the amount. Or you could say, what is 6 divided by 56? That if you want a fraction, you have to reduce it. That would be 3 out of 28. 3 chances out of 28. And then what about selecting an orange and then an apple? See, this is dependent as well because you don't replace. You're still not replacing, right? We're not replacing the thing. So if I select an orange, well, there's 5 of them in the bag of 8 fruits. And now I select an apple. But now there's only 7 in the bag, and 3 of them are apples. So I could get an orange, and then I could get an apple, and that would be 15 on top of 56. Right? So what is that? 15 divided by 56. That's 26.8% of the time. 26.8% of the time. Right. So if you want to make a fraction, you can if you reduce it. If you want to make it into percent, you can. You just divide it, and then whatever decimal comes out to be, just move it over. You can leave it a decimal too. You'll see that sometimes they write the answers as decimals, other times they write the answers as percent, other times they write the answers as decimals, percents, or fractions. Yep. All right. So let's see if we can do one of these guys, huh? So we want to erase that stuff. What if they give you a chart? We want to look at this chart. Woo! There we go. Now then. A student must have a B average in all classes to qualify for an athletic team at Jefferson High School. And the table below shows the distribution of grades. So, field hockey students, 15% of them get, or 15 of their players have an A and 4 have a B. In basketball, 7 of the players have an A and 13 of the players have a B. And in football, 2 of the players have an A. 22 players have a B. What does that tell you about football players, huh? Okay, so we need to know the total. So we know that 15 plus 4, that is 19. And then 7 plus 13, that's 20. And then that's 24. So if we add all those together, 19 plus 20 plus 24, there's 63 total. 63 total student athletes. Okay? Student athletes. So, what's the probability? So I grab one of these kids. There's 63 kids to choose from. Right? So 63 is the bottom of the fraction. What's the probability that I have a field hockey player with a B average? Well, that would be 4 out of 63. What's the probability that he's an A student that plays football? Close my eyes. I have 63 names in a hat. What's the probability that he's an A student and he plays football? 2 chances out of 63. Yay! What's the probability that he has a B average and he does not play football? So you can't use these guys. A B average would be 17, right? 17 out of 63. 17 out of 63. Now you can make these little decimals or little numbers, it doesn't matter. 17 divided by 63, that would be 27% of the time. And then 2 divided by 63 would be 3.2% of the time. And then what was that one? 4 divided by 63 would be 6.3% of the time. So remember, the smaller, so it would be a very rare event to pick an A football student. But it would not be a rare event to pick a B average student that doesn't play football. Right? Let's look again. Let's get rid of that. Where's my eraser? I lost it already. Alrighty. And then we've got one more. There we go. One more. The 4 green marbles and 3 white marbles in the bag. So there's 7 total marbles. A white marble is randomly selected, so I reach in and grab a white marble. Then the green marble is selected. Oh, are these independent or dependent? It just depends if I replace it or not. And it tells you right here, I did not replace it. So that means it's dependent. Because the probability changes if I don't put the marble back in the bag. Right? What's the probability of this event occurring? Well, if I pick a white marble, that's 3 chances out of 7. Now, if I hold on to that white marble, there's only 6 marbles in the bag, and 4 of them are green. Right? So the chances of me getting a green one is better, right? So that's 12 chances out of 42, and then 12 chances out of 42 is 0.286, so that would be 28.6%, right? And this is the same thing if I divide by 2, I know that would be 2/7. So that would be 2/7 of the time, or 28% of the time, right? That's the ticket. All right, you should be able to do today's homework without any trouble at all. Bye-bye.